Welcome to Behavioral Patterns. In this video, we are looking at the strategy pattern, a technique that lets you define a family of algorithms, wrap each one behind a shared interface, and swap them in and out at runtime. By the end, you will be able to spot this pattern in a code base, write a minimal version yourself, and know exactly when it earns its place. Imagine you're building a sorting feature. First you need bubble sort, then merge sort, then a quick sort for large data sets. The natural instinct is to add an if-else for each one inside the same method. That works for 2 cases, but by the 5th variation, that method has become a wall of conditionals. Every new algorithm is a reason to touch and potentially break old code, and testing one path forces you to load all the others. Think of a GPS navigation app. The screen that draws your map is always the same, but behind the scenes there are several routing engines. One optimizes for speed, one for distance, one to avoid tolls. You tap a button, and the app swaps the engine. The display code has no idea which engine is running. It just asks for a route and gets one back. That is exactly the relationship the strategy pattern formalizes. The Gang of 4 defines strategy like this. Define a family of algorithms, encapsulate each one, and make them interchangeable. There are 3 named participants. The strategy interface declares the operation every algorithm must provide. Each concrete strategy is one implementation of that interface. The context is the object that needs an algorithm. It stores a reference to a strategy and delegates to it, so it never knows which concrete version it is working with. The client is the code that wires the right concrete strategy into the context. Let us walk through this top to bottom. First, we declare the strategy interface, sort strategy, with a single method called sort that takes an array of numbers and returns a sorted array. That one method is the contract every algorithm must honor. Then we write concrete strategy A, bubble sort, which implements the interface using the classic nested loop approach. It copies the input so it does not mutate the original, then bubbles values into place. Concrete strategy B, built-in sort, satisfies the exact same interface, but simply delegates to JavaScript's built-in sort. Notice, both classes are completely independent of each other. Next is the context, the sorter class. Its constructor accepts any sort strategy and stores it in a private field. The setStrategy method lets the strategy be replaced later, and the sort method just calls this .strategy.sort. It has no conditional logic, no knowledge of which algorithm it holds. Finally, the client creates a sorter, injects bubble sort, and calls sort. Then it calls setStrategy to swap in built-in sort and calls sort again. Same context, different behavior, no if-else in sight. The power here comes from programming to the interface, not the implementation. The context never imports bubble sort or built-in sort directly. It only knows about sort strategy. This means you can introduce a new algorithm, say radix sort, by writing one new class that implements sort strategy, and nothing else in the system needs to change. The trade-off is that the client, the code doing the wiring, must be aware of all available strategies. Someone has to make the choice, and that responsibility now lives with the caller rather than inside the context. Strategy earns its cost when you genuinely have a family of interchangeable behaviors that need to vary independently, especially if new variants keep being added or each one needs isolated testing. Skip it when there is really only one algorithm or when the difference is so small that a Boolean flag or a plain function parameter is clearer. Also worth noting, TypeScript functions are first-class values, so a one-method strategy interface can often be replaced by passing a function directly, simpler and equally flexible for small cases. To recap, strategy is about defining a family of algorithms behind one interface so that the context that uses them stays completely decoupled from any specific implementation. You swap behavior by swapping the object reference, not by branching. That makes the system open to new algorithms without touching existing code. Just remember, if you only have one algorithm today, and no real expectation of more, the pattern is overhead, not help.